All right, hey guys. Today we're going to talk, or in this video, we're going to talk about domain and range. Though we'll spend more time on domain uh, in this video. Um, before we get into it, I just want to mention that there's two different ways we'll think about domain at least. What we're really going to talk about today is mathematically defined ranges. We'll get to that in a second. But often the domain will be determined, and consequently the range will be determined by something in the real world, the demand of the real world, right? So if you have a function that's describing the altitude of an airplane, right? Or let's say, no, you have a function that's describing the pressure that your airplane experiences given an altitude. So the input's altitude and the output is pressure. Well, the domain is going to be whatever max and min altitude that plane experiences, right? And while the function might mathematically make sense for lots of different numbers, if our plane is only in some certain domain of altitudes, those are the only ones that make sense to talk about for the function. Or if you're timing, or you might have a function that says how much money you make given your input of hours worked times your hourly gives you how much money you make that day, right? Well, we can multiply negative numbers, but working negative hours doesn't really make sense. And so your domain would be positive numbers there. And there'd be some limit to how high you could get given how many hours you can work, things like that. So there will often be real world demand. And those would be given when the function is given, or something that you'd figure out from the context of the situation. So we're not going to talk about those situations today. What we're going to talk about instead are the domains demanded by what we see mathematically, something implied in the function itself. So just one really simple example. If our function is given to us as a table or a set of input-output pairs, maybe it's given as coordinate points. I'll just write this out this way, right? Maybe this is our function. Who knows what this might represent, right? But if I were to ask about the domain and range of this function, it's very straightforward. Our domain is just this set of four numbers that we have. If this is the entire function, then its domain is -2, 0, 7, and 9. And we could read its range. I typically put things in order. I don't think that's strictly required, but it's kind of nice for your audience to do it that way. And so there would be our range, right? The output values. And these little curly brackets, that's what we usually use when we're listing individual elements like this. That's at least one place that we use these brackets. So in this sort of question, it's very straightforward. Domain is our input values, range is our output values. So let's look at something a little more interesting. Let's look at an equation, a function that's given by an equation. So we might have the function f of x is equal to 2x cubed plus x, right? So here's our function. Its set of instructions is given an input. You take that input, you cube it, you double that result, and then you add the original input. That's how you get your output, right? So the domain question here is what inputs are we allowed to put into this, right? So when I say defined mathematically, I mean, is there something in this math that won't allow certain numbers and only allow other numbers, right? Well, in this case, all numbers we can cube, right? There's no number in the real numbers that we cannot cube. And once cubed, there's nothing we can't double and then add back itself. And so in the case of this function, the domain is all of the numbers. And there's a couple ways we can write that down. Sometimes we write an inequality. We might say we're looking at x between negative infinity and infinity. Notice those less than signs do not have or equal to's on them because infinity is not a number. X can never be equal to it. So we have X is a number. This is saying X is a number between negative infinity and infinity. We might also write this in interval notation where we write the upper and lower bounds. In this case, again, because infinity is not a number, I'm using the curved brackets. That's saying on this interval, don't include the endpoints. We'll see examples in a second where we do include them. But here we're not including the endpoints. There's also a way to write this down that we call set builder notation. We'll use those curly brackets again. And it's well, let me just write it and then I'll say it. So the way I would read this is something like all x values such that vertical line there we can read as such that x is between negative infinity and infinity, right? The set builder notation is you kind of give the name of the objects you're talking about, then there's this vertical line, and then some kind of description of which objects you're talking about. Usually that's an inequality, though. It could be something like I might have a function that only allows even numbers, and you could write x such that x is an even number. Using words is perfectly fine, or some other symbols. I'll put one more symbol here. Since we're talking about all the real numbers, we have a symbol for the real numbers, this fancy R that you'll see here and there. So I might use that on occasion. Okay, so this is a straightforward function. Any value will do. Let's look at some more functions. Let's look at something where we do have to consider some values that will not work. G of x is equal to 2 plus x over 1 minus x. Okay, so whenever we have a fraction, the thing we have to always ask ourselves is about the denominator and whether the denominator is 0, right? Or denominator can't be 0, I should say. And so when we ask about the domain of this function, the only thing we really have to worry about is whether that denominator is 0, right? In the numerator, we're adding 2 to a number. We can certainly do that. In the denominator, we can subtract any number from 1, and then we can divide any 2 numbers, except for the one case where we're dividing by 0, right? So a fraction with 0 in the denominators makes sense. So that's the one thing we don't have to worry about. And so you might be able to see exactly what that means in terms of x, but sometimes it might be more complicated. And so knowing the denominator can't be 0, what I'm trying to do is ensure that this is the case. And you can solve this just like you solve any equation. This just tells us that x can't be equal to 1. Often people will write the domain just like this. We typically put the x first. X is not equal to 1. When we write a statement like this, the convention is to assume everything else is fine. So we're working in the context of the real numbers. So if I write the domain is x is not 1, I'm saying everything else is fine, not 1 is all we need to know. We could write it in one of our other notations. So for instance, another way to write this would be we go from negative infinity to 1. We're not including 1. Or from 1 to infinity. So x can be a number between negative infinity and 1, so anything below 1. Or it can be a number larger than 1, between 1 and infinity, not equal to 1. Another way to write that or, we have this set. This is a symbol for union, and you can think of it as just saying or, negative infinity to 1 or 1 to infinity. You can also write this in and as an inequality or a set builder notation, right? But you can kind of see why we end up, when there's just like one value we want to exclude, why we might just, or rather write x is not equal to 1, because it just takes a lot of work to write all this. I'll mention too that I'm not saying anything about the range. We will kind of work on ranges as we get into each of the individual kinds of functions we're looking at. Right? We'd have to do some good thinking about g of x to determine what the outputs are for this function. It might be a little bit easier with f. We'll look at, this is a polynomial function. We'll look in more detail at these, but it'll turn out that the range of this kind of function is also going to be all real numbers, right? So I'll just use that symbol r, right? But that might not necessarily be the case for g of x. We'll look deeper into these are called rational functions. We'll see them later and look at that. Let's do another example where that you might be somewhat familiar with. Let's look at something like h of x. Let's just do x squared plus 2. Right? Our domain should be pretty straightforward. What numbers are we allowed to square and then add 2 to? Well, any of them. There's no number we can't do that to. So again, I'll use that r symbol. The domain is all real numbers. How about our range? Well, let's just do a little thinking here. What do we know about the number x squared? Regardless of what we put into it, I know that the smallest it can be is 0, right? Anything you put, if you put in any value that's not 0, you get a positive number out. And if you put in 0, you get 0. So the smallest x squared can be is 0. So if I'm taking numbers that are either 0 or larger and adding 2 to them, I'm always going to get numbers that are 2 or larger. Or another way to say it is I'm taking 2 and adding either nothing to it or something positive. So I can only get bigger than 2. Well, in that case, that means that the range is that our function is always going to be greater than or equal to 2. Right? The outputs are going to be greater than or equal to 2. We could also write this in the notation from 2 to infinity. Right? Now, here's an example where we're including the endpoint. That 2 is included in the range. H of 0 is equal to 2. That is an output value. So we include that 2. But we don't include infinity because, as I said, we can't actually include infinity. We're going to look at graphs in more detail in just a moment, but if you remember anything about parabola like this, or parabola like this, a quadratic, what its graph is a parabola. In this case, it would look something like this, where this is the point 0, 2. Right, so looking at it graphically, the output values are the y values. Every point on that graph has a y value that is greater than 2. Okay, let's look at another situation where we have to, let's just get a clean page before I start messing things up. Let's see, let's have the function L of x, which is equal to the square root of 3 minus 2x. Okay, so radicals, any roots are another place where we have to consider our inputs carefully. Specifically, even-powered roots. In this case, right, this is the exponent 1/2. If we also had a 4th root or a 6th root or an 8th root, exponents of 1/6 or 1/8, and so on. We can't have negative roots. We can't take the roots of negative numbers. And so we need to be sure that the input, sometimes called the argument of the radical, is not less than 0. In other words, 3 minus 2x needs to be greater than or equal to 0, right? 0 is fine, right? When we're dividing, we can't divide by 0, but we can certainly take the square root of 0. The square root of 0 is 0. And so we just need to solve this inequality. There's a couple of ways we can do it, but I'm just going to do it this way. Negative 2x is greater than or equal to negative 3. Divide by negative 2. And remember, when you divide, you need to reverse. When you divide by a negative, multiply or divide by a negative number, you need to reverse the sign of the inequality. So we get x is less than or equal to 3/2. Right? Otherwise, we end up with negative numbers in there, right? Like just to make it clear to us, let's put in a number bigger than 3/2. So bigger than 3/2, for instance, the number 2, we get 3 minus 2 times 2, or 4. 3 minus 4 is -1, and we try to take the square root of -1, and there's no number in the real numbers, so that when you multiply it by itself, you get -1. So there's our domain. We can write it as an inequality here. I could make this into set builder notation. I can write it as a interval notation. Oops, sorry, I did this backwards. We're not greater than 3/2. Pardon me. Let's do that again. We're going to be going from -infinity up to 3/2. Okay. So there is our set builder notation. Let's do 2 more using equations, and then we'll look at some graphs. So let's look at k of x is equal to 1 over the square root of x minus 1. So we got a couple of things going on here. We know we need to be careful with denominators when we've got denominators, when we've got fractions, and we know we have to be careful with radicals. So in this case, we need 2 things to be true. We need x minus 1, because of the radical, we need this to be greater than or equal to 0, right? Because we can't have a negative in there. However, we also need to make sure that the entire denominator is not 0. And so if x minus 1 is equal to 0, the square root of that will be 0, and we'll have a problem. So we have to actually take away that or equal to, because then we'd have a division by 0 problem. So now we simply solve this. We get x is greater than 1. In set builder notation, it's x such that x is greater than 1. As an interval, it would be 1 to infinity, right? We're not including the endpoint there, so I have the curved line, and there is our domain. And then finally, let me do one that's more complicated than we probably need right now. That we'll look at stuff like this in more detail later on, but I think it's worth seeing at least once just to start our brains mulling over this. Let's consider something like this. This is not as straightforward to think about. We see that radical. Well, let's start inside the radical first. X squared minus 1. We can square any number and subtract 1 from it. So that argument, the input to the square root, has no problem. But we know that we need that to be greater than or equal to 0, right? Which implies that we need x squared to be greater than or equal to 1. Right? Now, we can't solve this like a regular equation that we solve, right, where we might take the square root. So let's just think it through. So what we know is if we square a positive number, we get a positive number. If we square a negative number, we get a negative number. Let's think about the positive numbers first. I need to make sure I'm taking numbers and squaring them and getting things greater than 1. Well, think it through. For all the positive numbers, if you start with a number bigger than 1 and multiply it by itself, it's only going to get bigger. So certainly numbers bigger than 1 end up bigger than 1 when squared. If a number is smaller than 1, but again, we're only talking about positives, if you multiply a number smaller than 1 by itself, or if you multiply anything by something smaller than 1, it gets smaller. So if you're multiplying by something that starts out smaller than 1 and multiply it by something smaller than 1, it gets even smaller, so it's still going to be smaller than 1. Like 1/2 times 1/2 gives you 1/4. It's getting smaller. So numbers below 1 don't satisfy this for the positive numbers. And then clearly 1 satisfies this. 1 squared is 1. So part of our solution is that x has to be greater than or equal to 1. Now let's think about negative numbers. The easiest way, I think, to think about this is, well, we know that when we square, if we square the same numbers that we're talking about here, x values greater than or equal to 1, except they're negative, we're going to get the same results, right? 2 squared is 4, negative 2 squared is 4. 1.5 squared is 2.25. Negative 1.5 squared is 2.25. So we want the same numbers, except with negative signs. And what that would be, right, starting at -1 and getting bigger numbers, except they're negative, means less than or equal to -1, right? Like -2, -3, -4, and all the numbers in between, right? And so there would be our domain. Okay. We can write this in interval notation. This is a nice one. We're less than -1, so from -infinity to -1, including -1. We'll use that union symbol and think of it as an or one is, or one greater than 1. Okay. Notice in all these intervals, we're always starting with the smallest and getting larger as we move to the right, even across that union symbol, right? That's what we're doing. It's really just kind of going with the flow. When we think of a number line, we have 0 in the middle, 1, 2, 3, right? -1, -2, -3, -4. It's just right that you as you move left to right, you get larger. We're doing the same kind of ordering when we write our interval notation. Okay. There is that's a complicated one. We'll dig into some of that stuff later on when we study some of these functions, either in this course or in later courses, in more detail. Let's now look at a few graphs. Oops. All right. So let's start with this graph. There's a function. We want to figure out the domain of this graph. All right, I'll just write it as f of x, and I'm just going to write is the graphed function. Okay. So our domain is the input functions, values, right? So if we look at this graph, right, we just have to think, right now, this function, we're looking at the entire function with this graph. And we just want to look at, we're imagining all of the x coordinates of this graph. In fact, let's do this really quick. Whoops, that's not what I want. Okay. Sorry about that red dot. I'm just going to leave it because it's a pain to get rid of it. Let me add something to this. Oh, it's driving me crazy. Okay, so let's put in a one, 5. All right, maybe this will help. So here I have a little scrolling point that goes through the graph. What I'm imagining is I just want to write down all of the x values that these points take on. In fact, let's label this. Just, as we scroll through this, we're hitting every single number as we go through, right? So in the case of this graph, I've labeled these endpoints. We're starting at 1, 3, move around quite a bit and get to 5.5, 10.875, right? So we're only caring about the x values, and in this case, we've hit every x value from 1 to 5.5. So that is our domain. Now let's think about the range as we go through this thing, right? It doesn't matter that we go up and down several times. What we're asking ourselves is, do we hit what values does our function hit? What outputs do we have? And so what we should think about when we look at this thing is, where is it the biggest and where is it the smallest, right? We've got this little peak right here, which we call a local maximum. That means just nearby, it's the biggest peak, right? Nearby can just kind of be any little space around it. Just the points next to it are all smaller than it. Here we clearly have the bottom of our function, right? And this doesn't hit a some nice integer or something like that. I found the exact value, and it involves a square. It's an irrational number, meaning the decimal goes on forever. It's the square root of, I think, 52 is involved, something like that. So we're just going to approximate it by looking. Notice we're down at -3. Let's just call it -3.1. Let's just round to the nearest tenth. Well, actually, let's go to 3 decimal places because we know that where the peak is. So we'll do -3.06. We'll round it to 5. So our range has as its bottom -3.065. Okay, right, approximately. And we're including that point because we see right there, that's the point. We're hitting that right there, or at least approximately hitting it. And then at the end, we hit our maximum of 10.875. Right, and so there's our range from the graph. Okay, how far down does it go? How far up does it go? And does it hit every value in between, right? We have to be careful of that. For example, here's an extreme counterexample to that, the idea that we're hitting every value in between. Here's a different function. This is called the floor function. What the floor function does is, if you give it a number, it spits back the greatest integer below that number. So for example, the greatest integer below or equal to that number. So if I give it the number 1.5, the largest integer less than or equal to 1.5 is 1. If I give it 0.397, the largest integer less than or equal to 0.397 is 0. So it drops every number down to the next highest integer. If you give it an integer, right, it's got that equal into it. So if I give it the number 2, it looks for the next, the highest integer less than or equal to 2, and that is 2 itself is less than or equal to 2. So what that means is, let's right, if I pick any point on the graph here, right, between 0 and 1, the next integer below is going to be 0. So notice all of these values from 0 to 0.99999 as far as you want, spit back 0 because 0 is below them. But once you hit 1, right, notice this open circle, that is just showing you the point where we kind of where that graph ends there, but we're not including that point on the graph. So whoops, didn't zoom, sorry. The input 1 does not spit out the output 0. That's why that hole's there. It's just marking that point because that's where the graph ends. Then the circle above it is filled in because inputting 1 outputs 1. Right? So that's where our graph continues. If we didn't have that open circle, it might be a little bit unclear exactly what's happening. So this is the convention when we have these jumps. And now when we start putting in numbers between 1 and 2, anything less than 2, we're bigger than 1 but less than 2, will spit back a 1. 1.55. The first integer below it is 1, right? 1.74, the first integer below it is 1. And so for all of these inputs, the output is 1. And then we jump to 2, and then we jump to 3, and so on. So I've set this function up arbitrarily. Just call it the floor function. I think sometimes people use this symbol. I don't know how to type that. I've set it up arbitrarily so that the domain, it goes from 0 to 5. And we can just see that in the graph, right? There's inputs from 0 to 1, then 1 to 2, then 2 to 3, 3 to 4, and 4 to 5. And our graph stops. That's all of the graph. The floor function can work for all numbers, but I set it up just to be from 0 to 5. The range is very different than the ranges we've seen. It's not a continuum of numbers. It's not all the numbers right above this. We have this range from -3 point whatever up to 10 point something, right? And all the numbers in between. Here we have a very short list of outputs. Our outputs are 0, 1, 2, 3, and 4. Oh yeah, I didn't include 5. Apologies, because if I included 5, we would have one output of 5, because inputting 5 would output 5. But I didn't include 5 because our function ends there at 4. That circle is closed, so there's no wide. There we go. don't like how the line was going into those circles. Right, so we have to just list the values here because we've just got this finite list. I can't say something like it goes from 0 to 5, or sorry, 0 to 4. I don't know why I wrote 5. 0 to 5, right? I can't use this notation here. That implies all the numbers we are talking about, 0, 1, 2, 3. Why did I write 5 again? Sorry. 0 to 4. But it also means our range would include something like 1.5. But if you look, there's no output. There's no point on this graph with an output of 1.5. That would be something at, right? If I put in y equals 1.5, it would have to have a point in somewhere on that purple line as part of its graph, and it doesn't. And so that can't be part of the range. All right. So this is wrong. Okay. This is an interesting kind of function. I mean, it's interesting in its own right. This is, in fact, the kind of function I use for your grading scheme. A little step function. So, like at the end of the quarter, you get a percentage, and I'll convert that percentage to something on the 4.0 scale. And so, if you have somewhere between, let's say, let's look at one of these. All right, a 78.5 and a 79, between a 78.5 and a 79.5. So what that means is I round your percentage. So 78.5 would be rounded up to a 79. So that's including the 78.5. On the other end, 79.5, I'm not including the 0.5. So anything below 79.5, so 79.4 something, is rounded down to 79. That's part of the 79%. That equates to a 2.4. And then if you jump up between a 79.5 and an 80.5, right, rounded to 80, you get a 2.5. And then you jump, so at each percentage, you jump up to another value. The output is always going to be numbers between, it's going to be 0, 1.0, 1.1, 1.2, 1.3, on up to 4.0. But none of the numbers in between. Nobody's getting a 3.56. Nobody's getting a 3.5779 or something like that, right? It's always going to be one of those values that we've talked about. So, something to the nothing beyond the 10th place. And so we have the same kind of step function. But beyond that, these both belong to a class of functions that we call piecewise functions, right? So let's look at another more common kind of piecewise function. This one here, let's see, let's make some space. So it's a little hard to read in Desmos. They have their own way of writing them, but the typical way we display these functions, this function is negative x plus 3 squared plus 3. And I'll explain all this in a second. If x is less than or equal to negative 2, and 2x plus 8 if x is greater than negative 2. So we'll talk about the domain and range of this function, but I just want to make it clear what a piecewise function is. We've talked about functions being sets of instructions, right? The function y equals 3x minus 7 tells you to triple a number and then subtract 7 from it, right? Take an input, triple it, subtract 7, return the output. That's the set of instructions. This a piecewise function is the same thing. It's a set of instructions. It just has a very special kind of instruction in the beginning, which is look at the input and categorize it, right? And so we have two different categories, less than or equal to negative 2 and greater than negative 2, right? And depending on what category it is, it falls into different instructions, right? This is I mean, we follow instructions like this all the time, right? I might divide my students. I might have files with A through K, and then L through Z. And so if I'm filing them, my instructions are look at the last name, look at the letter. If it's in one category, put it in this box. If it's in another category, put it in this box. It's the same idea. So if you look at your number, your input, and it's less than -2, you do this to it. This, it's a complicated instruction. You add 3 to it, you square what you get, you make it negative, and then you add 3 again. That's the instruction. But first you categorized it. If it ends up in the category greater than -2, you double it and add 8. You get this other set of instructions. So your first step is categorizing the input. Graphically, what that means is what we see here, why we call them piecewise. We get these pieces of functions, right? So for the numbers less than or equal to -2, right? That's a parabola facing down, right? So right now I've got it graphed for all numbers, but we stop graphing it at -2, right? Oh, I already took those in. There we go. I made a nice little dotted thing. Right, so we stop graphing it there because our instruction doesn't let us do that for numbers bigger than -2. And the same thing for this line. We can graph this line for all numbers, 2x plus 8, but for the piecewise function, because of that sorting condition in the beginning, we don't do this for numbers less than -2. So these dotted parts are the parts of the graphs we're throwing away, and we just keep these pieces that become our new function. Notice that open circle, closed circle thing again. We have this closed circle down here at -2, 2, because we're including, for the value -2, we're using the parabola, this -x plus 3 squared plus 3 instruction. And so that point, that is what you do. The value that shows up right here of 2 is gotten by putting it into this, this negative x plus 3 squared plus 3. If you put in -2 to 2x plus 8, out pops 4, but we're not including that value. We have the open circle there. But once you get bigger than -2, then we start including all those points on the line, right? All these other, right? Everything up to 2. Right, so you notice it jumps down to -2, 2 to tell us that the function's actually continuing over there. If we're bigger than -2, it spits out the values up here and then jumps down as soon as we hit -2. Okay. So in this case, let's look at the domain of this function. Right. It's implied by this graph, right? And this is where things get a little bit tricky, but when you see if no other instructions are given and I'm asking you to find a domain from this graph, you can just assume if I don't draw endpoints on the outside that it keeps going forever. And so that implies we can put in any number we want and get out a value, which is also supported by this, the way I've written it down here. So our domain is all real numbers. I'll use that symbol again. Our range is a little bit trickier. Let's look at the bottom half of the graph. Well, if we assume, and in this case, that's a correct assumption, that the graph just keeps going down forever, there's no value down there that we don't get to, right? So we're going to be, I'm going to say starting at -infinity, even though that's a nonsense statement, right? But it's just a way of saying we can get as large a negative number as you want, right? But we never get bigger on this half of the graph than the output of 3, right? The top of this piece is right at 3. That's our vertex of that parabola, is at 3. And so there's our, we go to 3. Then we skip over a bunch of numbers, right? Because between 3 and 4, right, there's the output 3 is at the top here. The outputs over here are all less than 3, so those aren't going to change anything. Then we have this jump up to 4, but we're not including 4. And then after that, it just keeps going forever. Use that union symbol again, right? So this is a very strange sort of domain from all the numbers included, all the numbers below 3, including 3, and then all the numbers greater than 4, excluding 4. Okay, so we just have to kind of dig through this picture to understand what's going on there. All right, let's look at one more complicated function just to see. We won't do too much with this, but I just want to point this out. All right, here's another piecewise function, and my only point with this one, I just want us to note that our piecewise functions can have more than two categories, right? This piecewise function has four categories. It's a particular line right here. I can put in all the original functions. It's these four functions, right? They all happen to be lines in this case, but then we just take pieces of them, right? So it's one line from 0 to 3, then from 3 to 4, it's a horizontal line, from 4 to 6, it's a different line, and from 6 to 12, it's yet another line. So we can have as many categories as we want, right? Similar to my grading scheme, right? Where I've got a lot of categories, 0, 1, 1.1, 1.2, 1.3, all the way up to 4.0, however many that is. So our piecewise functions can get relatively large. Okay, I think that is all I have to say for this one. Thanks, everyone. I'll see you next